In this scenario, we're going to actually do another attitude feedback once again. But this time, instead of just having an external control torque applied to the spacecraft, we're actually going to do something more realistic and include reaction wheel dynamics. So there's a variety of different configurations we can talk to. We've seen one other effector so far, which is the external force torque module. And we've discussed how this has to be added to the task so it gets updated, but also attached to the spacecraft so the spacecraft knows which effectors to call. This is part of the modular dynamics that we have. Here we'll be doing the same thing with reaction wheels. And in fact, how do we make clusters of reaction wheels? Looking over the basic simulation scenario, we'll have a single task, single process, spacecraft with Earth, simple nav providing the attitude, which we need for attitude tracking error, and also inertial 3D for the attitude reference. MRP feedback provides a required control torque that before we just fed directly to an external force torque module. Now we're going to take this control torque that needs to be created with reaction wheels, run it through a reaction wheel motor torque module. This maps the control torque onto the 3, 4, 6 different wheels that you have using the least squares inverse. And then this reaction wheel motor voltage and reaction wheel voltage interface, those are optional modules. There'll be a simulation flag, because we can take those motor torques and directly control the reaction wheel torques, which have been added to the spacecraft, or we can create basically a digital to voltage interface. You can specify voltage behavior and then send a voltage command to a voltage to digital, a digital D to A interface that turns it into an actual torque command, a voltage, and then that's what drives it. So we'll see both. There'll be a few if statements in there. And when you run it, there's a bunch of flags setting up reaction wheels. Setting up reaction wheels, there's a factory class, just like with gravity. We had a gravity factory class that made life easier. We didn't have to remember all these subcommands and how to do things. The same thing will be true with these reaction wheels. We have some defaults like the Honeywell HR16 and a few others, but you can also just make your own custom wheels if you want to. You can override anything. Yeah, so let's just go straight to the Python code and see how this all comes together. So there will be a use simple jitter flag if we want to specify jitter. This model there's a balanced wheel which has no jitter, simple jitter flag where you end up with something that uses external forces and torques acting on the craft but are proportional to the wheel speed. So it's like an imbalanced washing machine thing rattling around. You can do that. And there's a flag for a reaction wheel voltage input that we discussed as extra modules that do a D to A to D conversion. So single process, single task. So we're going to skim down. We're going to run it for 10 minutes. Again, 10 Hertz integration time step. We set up the spacecraft, pretty straightforward here. Grav factory, we make Earth, add the gravity effectors to the spacecraft object. Now, here's the new stuff. We're gonna include the sim include reaction wheel. This allows you to create reaction wheel dynamics devices and facilitates that. One of them, for example, is these variable models. We have one thing called balanced wheels. We can also do reaction wheels simple. So I'm setting this up and I'm always providing it. And let's jump ahead and go back. That might be easier. If you look at these lines here, they talk about how to create a reaction wheel. So like we do create Earth, create Sun, and out comes a handle, and you can override some parameters of that data package that you got back. The same is true here with these reaction wheels. It creates them, and if you want to override something, you've got RW1 dot, you could change your max speed, your max torque, the friction coefficient, all of that. The first argument is the type. So there are several different types pre-programmed. Let's just look at the reaction wheel command, that create command. If I do this one, and at some point in the code, where is it? I've already gone past it. There's an eval command. There we go, here. And the type that you provides, it will simply look for a method of that name, and it'll pre-populate it with stuff that we need. So here you can see, for example, the Honeywell HR16. It specifies 6,000 RPM as the max speed you can have. The max torque is 0.2. The minimum torque is specified here. Some Coulomb friction is set up. And then you have other options like large, medium, and small momentum. So depending on the max momentum type, you have to specify either 100, 75, or 50 Newton meter second momentum capacity. That's the three commercial products. It sets up the mass and these imbalance coefficients for each one of them. If you have an HR14, similarly, it'll specify some of these parameters of the commercial public spec sheet. The HR12 is here. There's a Blue Canyon one that's been used for small satellites, which is convenient. But there's also custom, which basically gives you back a blank one. And then it's up to you to make sure you provide enough information that will actually populate the reaction wheel module. So if you have something that looks close to the Blue Canyon, you could then create that and override it, or just do everything custom, as you can see here. So anyway, that hopefully made some sense. So that's the create command. Second one is the axis. So this is going to line up with B1, or the first axis, or called x-axis sometimes. 0, 1, 0 is the second, 0, 0, third is the third. So I just have a nice triad, which are orthogonal with my body frame. The HR16 does expect you to specify max momentum, because they commercially come in 50, 75, and 100 Newton meter second capacities. I'm specifying also, this is optional, the initial wheel speed, and this is actually given in RPMs, because that's typically how we discuss wheels. And I'm also providing it this model, which is either a balanced wheel or the simple jitter. There's also a fully coupled jitter that we could do. It takes a lot more CPU to compute that one. If you don't specify the reaction wheel model, then by default, you will get balanced wheels. So if you didn't give this one, you will have balanced wheels automatically. Now, what's cool with reaction wheels, it's smart enough that if you have a balanced wheel, we don't care about the actual orientation of the wheel. We just care about big omega, the wheel speed. So there's one state to integrate per wheel. If you have an imbalanced wheel, you do care about the angle, because it dictates where that external force is going to act. Or if you have the fully coupled one, then you'd also care about attitude of the wheel and rate of the wheel. So if you have an imbalanced model, the reaction wheel will automatically request two states from the state engine. You don't have to do anything. It just happens under the hood. If it's a balanced wheel, it would simply request one state, big omega, the wheel speed. So there's some cool magic there. But again, there's lots of variables. Some of them are actually defined here as well, that you can set up friction, minimum torque, different ratios, where it's at. Where the wheel is at only matters if you have imbalances happening, because that affects the torques acting on the wheel. So there's some stuff you can read up on the documentation of these wheels as well. So here we did our first wheel, we did our second wheel, all the same stuff except for different initial speed and a different axis. We don't want all wheels to line up with the same axis, because that wouldn't be very useful. And the third wheel has a unique axis, and we chose to give it 300 RPM initial speed, and also actually an offset. This will have an impact on your torques that this imbalanced wheel will generate. So this is just an example scenario. The factory class, again, think of these create, like create Earth, create Sun, create this, and then it has internally, it just creates a list, a dictionary list of these. If you want to know how many wheels did you actually add in the simulation, you can always call the get number of devices, and it'll return a number. Say, okay, in this case, you have three wheels. That's nice, because sometimes when you make simulations, you may have 3, you may have 4. And so instead of looping and hard coding 3 or 4, if you get this value, you will, if I just added one more wheel, the rest of the scripts, the plotting, everything loops over the number of wheels that were added, not a hard coded value. So it's just a convenience. Now, how do we add this? This is just in the factory class right now. Nothing's actually to Basilisk. So we have to create an effector. So like with external force torque effector, effectors are things that affect the spacecraft differential equations, the spacecraft dynamics. And there's one called reaction wheel state effector. And we create an instance. To that, you then, it's basically a cluster of wheels that you generate. And you then add individual wheels. And this is an effector that you then get an update cycle. You have to add it to a task, do all those things. So right now we just created the Basilisk effector. We added the model tag. And then there's a reactional factory class that's handy, because it will do a lot of the under the hood stuff, like adding these to a spacecraft and setting the model tag and all of this. So if we go look at that, you can see here, whatever I told the space, the model tag for the spacecraft, it'll use something similar now for the reaction wheels. And to give it labels, I give it the reactional state effector, and I need to give it the spacecraft object as well. Let's go look at that command, add spacecraft to the model tag. This and the spacecraft comes in, it sets the model tag, it loops through the reaction wheel factory dictionary list, pulls out all the items, and then it calls the add reaction wheel command of the reaction wheel effector. Again, the effector is actually a cluster of wheels. It's usually like an RWA reaction wheel assembly. You don't just get one, you get 3 or 4 or 6 or something. So here it loops through what you set up and it will add them automatically. And we also have to add the reaction wheel effector as a state effector to the spacecraft. So for the spacecraft we provided, there's a command called add state effector. This is different than external force torque. That one was a dynamic effector. A state effector is a state that actually has differential equations it has to solve. So they're a little bit more complex under the hood. Anyway, you can read the papers on this topic if you want to get all the mathy details, but it's quite extensive. So this one has states, so it's an add state effector, and that's what add to spacecraft does. You don't have to call this command. You could also just run this directly if you wish. So now the spacecraft knows what wheels you've attached to it because we've called this line here. We still have to add the reaction wheel effector to a task, and we do this here with this line. If we didn't do this, then the reaction wheels would never be calling an update cycle. And that means the reaction wheels actually log in the update cycle all the states. This is the command, this is the wheel speed, everything. There's messages that are created as an output for logging. And that only happens when you run update. So if you forget this line, the control may work, but you can't log anything of the wheel. So now the physics of the wheels are created. If we needed the voltage interface for the reaction wheels, so if that simulation flag is thrown, we create this Basilisk module, we set the module tag. You can read the documentation for this module, but you can set some gains on what the voltage to torque interface should look like. There's different behaviors you can set up. This is just using a simple, linear relationship here. And they're usually pretty well calibrated for that. And then I add that to the task. Good, then we still need simple nav to pick up the actual spacecraft states and convert them into something that flight software can use. And then the rest of it, this is flight software modules. We are setting up here the inertial 3D. That's what we've done before. Attitude tracking, we did before. MRP feedback, we did that before. But the output of MRP feedback, which is a commanded torque, external torque that has to act onto the system, is now actually going to be connected to another module called reactional motor torque. So if you have 3 wheels, and they could be lined up in any orientation. So if your control torque has to be 1, 2, 3 along the B1, B2, B3 axis, and you have wheels that are 4 wheels that are lined up in a pyramid, you're going to have to map that torque vector onto these 4 wheels. And if it's a redundant system, it will use the least squares inverse to get the best fit. If it's a unique system, then it does exactly what it is. If it's under-actuated, it will actually do the best mapping it can, but you won't get exactly that control torque back. But that's what this module does. So it's a C module. So with the usual setup, we create it, add a model tag, and add it to the task. Then there's control axes, which are actually the first 3 variables, the first axis, then the second axis, then the third. So this provides 3 different vectors. That means I'm going to have 3 axes I'm going to control. If you needed reaction wheels only control a subset of all possible torques, maybe the torques about X and Y, but not Z, you could leave out these last 3 values and it wouldn't control torques about that axis. So it's convenient because sometimes we don't have full actuation with the reaction wheel cluster. Or you may only choose to actuate part of the control torque with reaction wheels, and maybe one part is going to come from thrusters because that torque might be much bigger than what reaction wheels could do. So again, you can read up on that, but here I am specifying the control axis, which you should, for the reaction wheel motor torque configuration. So it takes the actual control torque and it will fit it in there. The last one, when we have then motor torques, we have to map those to voltages. The analog to digital interface we've already done. This is the flight software digital to analog version. And essentially you set its module, and you have to specify also a minimum and maximum voltage. And you can go read in the module how to create that if you want to use it. The rest of it now, we're almost there. We have to set up recorders and obviously subscribe to different stuff still. And we'll talk about that. These recorders for the modules are pretty straightforward. What is less straightforward maybe is the Reactional factory. Right? We added all these wheels to the effectors. So these wheels are like embedded in this effector. And so each wheel, it's with the effector, it will create an output message per wheel. So if you have 4 wheels, it'll make 4 output messages. And so we can record those by recording the reactional state effector dot reaction wheel out messages. Then you have to give it which one, the 0th, 1st, 2nd, 3rd order, and set up a recorder. Here I chose to make a list of recorder elements just so I don't have to have unique names for the first wheel, the second wheel, the third wheel. It's just a list of however many wheels I have. You don't have to do this, but this was actually quite convenient. So it loops through the number of wheels that were set up, and it creates a list of reaction wheel state recorders. If we have the voltage interface, it also records that one. Then MRP feedback did need this vehicle configuration message like before, so we can create that. And then let's see, flight software will actually need a message like with vehicle configuration. What is the inertia? Flight software will need to know how have you configured your wheels. And so with the inertia, you can specify the true inertia in your simulation, and in flight software, if you want to, you could make a slightly corrupted version, to check for robustness. With reaction wheels, you want to do the same thing. So there's 2 different ways we can create this message. It's a standalone message like vehicle config data, but we can use the flight software setup. There's a command that's called clear setup. This is handy if you're running this in a Monte Carlo sense or lots of different iterations where you're resetting the simulation script and running it over and over again. This will basically, the clear setup will clear out the dictionary list and make sure you have an empty set of items. And then in this method, I am looping through the reaction wheel factory, which was, the physical devices being simulated. The flight software setup, this is just in flight code. Where do I think this is? And we need limited information, maybe like what the max torque is, and what's the axis, and maybe what's the max speed or something. We'll see. So what I'm going to do is I'm going to loop through, and there's a flight software setup for reaction wheels .create, where you have to give it the axes, and I'm converting that into an eigenvector that we need for the interface. I need the inertia, and I believe, let's see this last one, I forget. The last one is the max torque. So by default, there is no max torque, it's set to nan. But if you specify it, which we do here, there would be a max torque. And if you ask for anything bigger, it'll just saturate at 0.2 magnitude. So you can loop through this. This will create a list inside this script. And then you can do write configuration message, and it will create this message in that one. If you go look at it, it loops through, pulls everything out, sets it up, the right message type, populates all that information that was created, disowns it so you can edit it from the outside, and it makes that message. And I'm calling that flight software reaction wheel parameter message 1. That's the first way to do it. I like this way because I'm taking the truth states. This is what was set up in the simulation. I'm pulling that directly now from the reaction wheel factory class. And if I want to make my inertia 2% bigger, I just do this in .js times 1.02. I could literally just do this, and immediately I'd have inertias in the flight code where they think it is 2% bigger than it really is. And you can do robustness checks. The second method in the reaction wheel factory, there's a convenience method built in, said config get config message, and it does something similar. It pulls, since the reaction wheel factory knows the true states of the simulation, it pulls all the true states and assembles the corresponding flight software message that you would have to create, and that's this one, and it returns it. And so you can just call it in one line, which is kind of nice and clean and simple, and it returns that message, and then we'll connect to it. So this line is just that lets you, if you want to play with this script, you can either have it use the second method, that is the true one, or the first one, and that should give you identical results. If you want to use the first method, at least this shows you a manual way that you can actually take truth, corrupt it, and then set your flight software message. So, as always, lots of ways to do it. So now we have all the messages that we need. Setting up initial conditions, pretty straightforward. We're doing our orbit elements, get position, velocity. We also have initial attitude and attitude rate, so it'll have to stabilize with wheels, pick up whatever initial momentum it has and absorb it into the wheels. Then there's the enable visualization. We give it a spacecraft object. From here, we pull all the spacecraft states, but it also knows what spacecraft, what gravity effector you added to the spacecraft. Similarly, if we have reaction wheel state effectors, there's an optional command that you can provide, and this will then make this interface pull the corresponding reaction wheel state effector information. This is for a single spacecraft. You can look at the documentation for this interface, or just scripting wizard. That's where you'll find all these different arguments you can have for enable unity visualization. So this will allow us to visualize it. Now we have to connect messages. This is all pretty much like before, except for there's two optional ones. Now that we have reaction wheels, we want to read in the reaction wheel parameters. This is why MRP feedback, if we have wheels, it needs to know how those wheels oriented. So it needs to read in that configuration, that flight software message that specifies what wheels you have. Also, it needs to read in the wheel speeds, and that's an output. The reaction wheel state effector has an output message which includes an array of wheel speeds for all the reaction wheels. So just connecting that to the module will give you access to all the wheel speeds that are in this flight system. Then, this message is used in two places here, as you can see, because we need to know when we map the external control torque onto the sets of wheel axes, spin axes. We need to know how those are lined up. That same message gets also read into this module. And it also needs to know, it's actually, the input message has to be connected to the MRP output. So that required control torque gets read into the reaction wheel motor torque config. Then, if we're not using the voltage interface, it's pretty straightforward. Then what we have is the reaction wheel state effector. It has an input message, which is again an array of motor torques. And we subscribe to the reaction wheel motor torque config. This is what mapped to motor torques in flight software, and its output message basically lines up with this input message, and we subscribe from one to the other. If we have the voltage interface, then we have to still go, that reaction motor torque gets read in to the voltage. That's the digital to analog converter. And this one also needs to know where the wheels are. So it reads into that message. And the analog to digital converter on the receiving end needs to read in that voltage message, and the state effector reads then the commanded torque. This is basically motor model directly. So that's the voltage to the analog to digital interface of the reaction wheel motor. So you can look at how those are configured. The rest of it now, where everything's connected, everything's initialized, everything has recorders, you can start to initialize, run the simulation, pull the data, and plot. If you want to look at this, there's different ways to plot this. I'll run this once here quickly. The script, you will see it runs. You can see the reaction wheel voltage being recorded here. You can also see the reaction wheel speeds, how to go. I've chosen to plot them in RPM, not in radians per second. With tracking errors, we do stabilize, and that's nice. The motor torques, I'm plotting actually both the commanded motor torques, which you exceed, they exceed the actual implementable motor torques. We set 0.2 Newton meters as the maximum torque these wheels could produce. So in this plot, it's handy because the dashed line is what the control commands, and this is the solid line is what you actually get. So this is an illustration of a saturated feedback control simulation. And then the attitudes, you can see the MRPs, they do converge. It takes a little bit longer because we saturate, but we do converge to 0. Now, if you bring this up in Wizard, I'm going to load up this particular scenario. Let's see, this would be attitude, feedback, reaction wheels. should be this one. And you can see here, initially had a different attitude than we wanted. So it's actually going to start to stabilize and go there. Under actuators, you can bring up a panel or visualize the wheels. The wheels are kind of cool because it gives you a heads up version and the color correlates to the speed. Now this wheel here is going much faster. The blues are the slow speeds, reds would be super fast, close to basically rainbow. Blue being near zero, but red would be now near saturation. And so you can see here in the panel as well, if you click the click marks, you can see actual speed and the torques being applied. And so now you can see the attitude stabilizing and everything kind of looks good. If we go way back to the beginning, they were all near zero. They had pretty low speeds. And as it absorbs the momentum of the initial tumble, it goes into the wheels and you can get a nice heads up display of where that momentum ends up settling. Right now, it was pretty even. But you can see we're torquing much harder on some of these wheels and the wheel speeds on some of them is going up quite a bit higher. Yeah, the speed is in blue, actually, yes. But some of them are higher than others. And that's what you see. Anyway, these are just great to put this all in context. So, summing it up, what did we learn here? The key thing here is how to add reaction wheel devices. They're effectors, so you have to add them to a task, the reaction wheel effector, but also connect the effector to the spacecraft. That's a key component. There's always two things you have to do with effectors. But fortunately, we have the reaction wheel factory class, like with the gravity factory class, that makes it simpler, and I highly encourage you to use these factory classes. The rest of it, MRP feedback was the same. We just have this extra module, and you can go look at the details of it, where it converts the control torque into motor torques, and then you can either directly drive that reaction wheel cluster with those commanded torques or go through a voltage interface. This simulation script shows both. Anyway, hope you enjoyed.